All right, so we are continuing with our alternative solution approach, stress-based approach. And so last time, we essentially formulated a different way to approach our problem. And this different way is to start from the outset, not with the displacement, but with the stress. Okay? So we are going to somehow propose a form of the stress. And the idea is that in order to be able to work with this concept, we would like to make sure from the outset that the stress satisfies, okay, from the outset, so a priori, it satisfies equilibrium. Okay, so we're not going to worry about equilibrium. Unlike the displacement-based approach, in the displacement-based approach, equilibrium is what closes the loop. It allows us to specify or restrict the form of the solution. We start with a relatively general but simplified form of the solution, and once we enforce equilibrium, we get the solution, the particular form. In this case, from the outset, we are going to assume that the stress, that's our primary solution field now, and that it satisfies equilibrium. But contrary to the displacement-based approach where compatibility is from the outset satisfied, in this case, we are going to enforce it. So in a sense, compatibility is the key equation that will allow us to restrict the particular form of the stress that we propose. So in the displacement-based approach, we start with a simplified form. We look at the symmetry of the problem, and then we calculate the strain, stress, enforce equilibrium. We close the loop, and we get the particular form of the solution. In this case, we start with a form of the stress. Eventually, you will see, I'll show examples. And we start with a form that is already simplified by looking at the symmetry of the problem, etc. And that form already satisfies equilibrium. We're going to enforce compatibility, and that will allow us to restrict that sort of form to the particular solution of the problem. Now, we will enforce compatibility, and that sort of ensures that there is a displacement field, but it will be up to us whether or not we want to construct that displacement field. But once we enforce it, we know that there's a physical displacement field that causes that stress field. So this is sort of the approach. Now, the key idea in making this concept work is called the Airy stress function. It's a, let me say, ingenious approach. It's quite old. But essentially, remember also that we are working with two-dimensional, intrinsically two-dimensional problems, which are either plain stress or strain. That's our setting. And essentially, what we did last time is we spent a lot of time framing a intrinsically two-dimensional problem in a generic setting where it could be either plain stress or strain. So we don't really worry about which is our particular setting. All we worry about is that we are in an intrinsically 2D setting, which could be plain stress or strain. So we are working in that setting in a stress-based solution strategy. Okay. And that is our solution diagram. Quite simple. So now, that's the idea, but let me enumerate the major steps, and then we will work on the major steps in this lecture step by step. So, step number one, I have to propose a form of the stress that a priori satisfies equilibrium. That's not trivial when you think about it, okay, because the equilibrium equation is a differential equation. So how can I propose a form of the stress that is quite general, that is able to encapsulate the particular solution of my problem, but at the same time, it is general enough so that it satisfies equilibrium. So that is the key concept of Airy stress function. So the first step is to start with a problem tailored. So this is also important. So remember, when I was solving for the pressure, thick-walled pressure pressurized sphere or the cylinder problem, I didn't start with the most general displacement field. I looked at the symmetry of the problem, and I simplified it to begin with. So my approach was sort of problem-tailored. In this case as well, I want to start with a form of the stress that is already problem-tailored. I put some insight into the problem by observing the symmetries, etc. So that is something we always have to do. Otherwise, it would be, might be impossible to solve the problem. So we start with a problem-tailored form for stress, which must satisfy equilibrium. So that's a challenge. That's the first one that we will meet. And the second step or challenge is to enforce compatibility to restrict this form. So that's the keyword, restrict. Okay, so it's a relatively general form, functional form, satisfies equilibrium, but that general functional form could possibly be the solution of different problems, but I have a particular problem, and that particular problem eventually will have a certain mechanics embedded in it, and compatibility will sort of restrict that form further. And finally, I know, because I have enforced compatibility, I know that there is a displacement field, and if necessary, I would like to be able to build it. Okay. So the key word is that it is guaranteed to exist, but if you're not interested, you do not necessarily need to construct it. Okay? Because essentially, by the time we're done with step 2, we will have the stress field. I know what it is. So 3 is sort of something extra we might be interested in. But of course, it's good to have some knowledge of how to work with that as well. And of course, somewhere here goes the boundary conditions. Remember, without the boundary conditions, it's hard to end up with the concrete, the final form of the solution. So boundary conditions are always implicit in there. So that's the idea, right? That's my solution strategy. That's the solution diagram. These are the 3 major steps. Okay? And the key idea that is sort of embedded throughout here is the concept of Airy stress function. So let us go through these steps one by one and simultaneously introduce the stress function idea. So let's be more specific and go with step number 1. So step number 1 is equilibrium, essentially. How do I ensure that I enforce equilibrium from the outset with this stress field, with a stress field? So the first step is that I will assume. Now, this is important. I am, at this stage, just going to write something, and you have to believe that it works, and it does work. So let's say that we assume that there exists an Airy stress function and I'm going to call this phi. And remember, we live in a 2-dimensional world presently. The 3rd dimension is just a byproduct. If we need it, we can work with it. But the solution lives in x1, x2 plane. Okay? We assume an Airy stress function such that. Okay? Okay, so here's the tricky part. Now, once I suppose I have that function, I will assume that the 1,1 component of the stress is calculated by taking the derivative of the stress function twice with respect to not the first, but actually the second coordinate. Now, plus I will add here another term, and it's a capital omega. I'll tell you what it is shortly. And sigma 2, is phi, comma, 1 plus capital omega. And the shear stress is found by minus phi, comma, 1, 2. Okay, so here we are eventually going to restrict ourselves to mechanics where there is a function omega which delivers the body force. Okay, so in other words, we will assume that F is equal to minus gradient capital omega. Okay, so this is, right, it's the potential. There may be no body force. If there is no body force, omega is not there, right? But in general, I would like to be able to work with body forces. And in fact, next time when we meet, I'm going to solve an example where we need the existence of a body force. But we are restricting the form of the body forces such that they are conservative. So conservative means, so that's the definition of conservative, remember from physics, if you have a force that is conservative or a vector field that is conservative, it comes from the gradient of some scalar potential. In this case, for convenience, we put also a minus sign or out of convention. Okay, so one very simple example would be, for instance, suppose that the x2 direction is the direction of gravity. Okay, so suppose x2 direction is actually the vertical direction. Then if we write omega equals rho g x2, then F is the gradient of the potential. And remember, this gradient also lives in 2D because we are in an intrinsically 2D world presently. F3 is, in fact, we admitted to be 0 from the outset. So now I have to take the gradient of this. And with respect to x1 is 0, so F1 is equal to 0. And F2 is minus gradient of this, or minus rho g. Okay? So that is the component of the gravity in the vertical direction. Right, so that's one example. So that's our only restriction. Okay, so we assume the existence of such a function. And with that function, we propose that we can calculate the stresses like this. So what's the deal? The deal is that if this is the case, in other words, if there exists a potential such that you can calculate the stresses like this, then equilibrium is a priori satisfied. In other words, you don't need to do anything. It's automatically set 0. Okay? So divergence sigma plus F is equal to 0. So let's show that. So we have two components, right? Again, two-dimensional word. We have divergence of sigma, so sigma 1, 1, comma 1, plus sigma 1, 2, comma 2, plus F1. We omitted the inertia, so that's equal to 0. And sigma 2, 1, comma 1, plus sigma 2, 2, comma 2, plus F2 is equal to 0. We have only two equilibrium equations presently. So all we have to do is substitute the form of sigma 1, 1 and 1, 2 and 2, 2 from these into these equilibrium equations. So let's do that. So this term here, it's equal to, so 1, 1, comma 1, phi, comma 2, 2, 1 plus omega, comma 1. Phi, comma 2, 2, 1 plus omega, comma 1. And sigma 1, 2, comma 2 minus phi, comma 1, 2, 2. And I'm assuming F1 is conservative, so it's minus omega comma 1. Right? And similarly, we can do the same thing on the right-hand side. Omega 2, 1, comma 1. So minus phi, comma 1, 2, 1. 2, 2, comma 2. So phi, comma 1, 1, 2 plus omega, comma 2. And F2 is minus omega, comma 2. And you probably already see that this term, right, we're always assuming our functions are nice and smooth, so it doesn't matter in which order we differentiate. I can cancel these two, these cancel, so it's a check. And presently here as well, 1, 2, 1, 1, 1, 2, they cancel, these two cancel. Again, it's a check. So if there exists such a stress function, equilibrium is satisfied. Now you might ask, whenever you deal with such mathematical concept, the question is it true that eventually when I formulate this, the problem like this, eventually, or the stress is like this, yeah, equilibrium is satisfied, etc., but I will carry on and enforce equilibrium. Eventually, I like to be able to find what that function is. So now, because what I've done is, instead of directly working with the stresses, I assume that omega is a given. It is the body force of the problem. I have converted the problem from finding the stresses, there are 3 of them, to finding a function phi. Will I be able to find it? Or does there exist such a function? And it turns out yes. So in other words, this is an idea that works. It's a very clever idea. But it is not the only approach to solving our 2-dimensional problems. So for plane stress and strain, there are other approaches. So we have to be also aware that this is only one idea, but it is one of the most, let me say, fundamental and elegant ideas. Okay? And that's what we are going to work with in our intrinsically 2D world. Okay, so that's the concept of an Airy stress function. So now, so if we go back to step 1, I am assuming that I can propose a form of the stress that a priori satisfies equilibrium. Now the diagram is slightly converted. What I'm really proposing is not sigma, but actually some stress function phi. Okay? And it does satisfy equilibrium. So it's gone. So now that I assume there is a phi, what I have to do is I need to go back to step I and also think about this. Okay? So it does satisfy equilibrium. There's a check there. When I try to solve my problem, I need to propose a form for phi that is problem-tailored, that is sufficiently general for the purposes of that problem, but not too general so as to make my life too difficult. Okay? So this underlying part is something we have to deal with problem by problem. Okay? So, but we're essentially done with step number 1. So now we will move on to step number 2. We want to enforce compatibility to further restrict or put restrictions on this Airy stress function. Could it be any function? It turns out no. It's subject to some restrictions, and that is foremost due to compatibility. All right. So let me move on to this board, and we'll take up step number 2. And that's compatibility. So I'll start here by defining the 2-dimensional Laplacian operator. This is to simplify our notation a little bit. And the Laplacian operator is, if you like, the square of the gradient. And so if you write it in components, and this is perhaps not too hard to remember, so Laplacian, so gradient squared, is you take the quantity, twice derivative with respect to 1, plus twice derivative with respect to 2. So if you actually go back and remember what we had written earlier, you will also notice that it is nothing but divergence applied to the gradient of the function. And again, you should remember that whenever I write these gradients, that we are in an intrinsically 2D world. So it's only with respect to coordinates x1 and x2. Okay. So that is the definition of the Laplacian. So now, let me also remind you from last time, we did something important for our purposes. Because we are working in a stress-based setting, I had my compatibility equations enforced on the strain. But now we're working in terms of stress. So what we did last time was, for these types of 2D problems, we formulated the compatibility requirement in terms of stress. Okay? And that compatibility requirement was the following. So it does work for plane stress or strain problems. Right? Omega was a constant, a function of simply the Poisson ratio that determines whether this is a plane stress or strain problem, stress, body force. And at this point, let me quickly also remind you that the original compatibility requirement is provided in terms of the strain. So it's a condition on the strain field. And it works for any problem. Whereas when I write this, I assume two things. One, we assume the isotropic linear elastic relation between stress and strain. Two, I already had assumed that equilibrium is satisfied from the outset. So those were things that were proposed with a view towards what we were trying to do. We are trying to satisfy equilibrium from the outset, so I already enforced it, and we are always in an isotropic linear elastic setting, so I also made use of that. Okay? So with those two assumptions, this is the form of the compatibility. And now what I will do is I will use our Airy stress function, what I have done in item 1. And so I will go ahead and plug in, instead of the stress, the forms for the stress components. So sigma 1, is phi, comma 2 plus omega. And sigma 2 is phi, comma 1 plus omega. And that's equal to minus 1 over omega. F1 is minus, so perhaps we can the minus sign there, so that makes a plus. So 1 over omega, comma 1, right? F1 is omega, comma 1, another 1. Then plus omega, comma 2. That's F2, comma 2. Okay. So now the reason I introduced the Laplacian operator is just to simplify this equality here. I now notice that this is the Laplacian of capital omega, the potential. And what I have here is Laplacian of phi plus 2 omega. So if I take Laplacian of 2 omega to the right-hand side, there is a 1 over omega factor, minus 2 appears. And on the left-hand side, I have gradient to the power 4 phi. Okay? So this is equivalent to gradient to the power 4 phi. 1 omega minus 2 Laplacian capital omega. And that is compatibility written in terms of the Airy stress function. Okay? So this clearly holds for all coordinate systems. So as usual, my derivation at some point assumes that it's a Cartesian coordinate system. That's what I always worked with last lecture as well. But eventually, once you write this, you can evaluate it in any coordinate system. So this is true for all coordinate systems. And if we want to work or find out what the Laplacian is in a, let's say, cylindrical coordinate system, I just need to look up in some reference book, and as long as I understand how to make use of this, its use is going to be sort of straightforward. Okay, so that's true for all coordinate system, and that's a PDE. Okay, that's a PDE for phi. So I can propose some form of the Airy stress function. Yes, that's how I calculate the stresses. And yes, equilibrium is satisfied a priori, but not every phi is permissible. Phi has to satisfy this requirement, and that will restrict further the possible form of phi that I can work with. All right. So the right-hand side is clear, right? This is the definition of the Laplacian. So on the left-hand side, let me make a quick note here. We have this operation. So this is square Laplacian applied twice. So if I call this some function, let's say capital phi, this therefore is equal to, by the definition of the Laplacian, capital phi, comma 1, 1, plus capital phi, comma 2, 2. But phi itself, capital phi itself, is the Laplacian of small phi. So then I have this equals small phi, comma 1, 1, plus small phi, comma 2, 2, right? Comma 1, 1. Okay. And then plus, again, small phi, comma 1, 1, plus small phi, comma 2, 2, comma 2, 2. Right? So if you collect terms, you will see that the fourth gradient of the Airy stress function is there is a phi, comma 4 derivatives with respect to 1. There is a phi, comma 4 derivatives with respect to 2. Okay. And finally, 2 derivatives with respect to 2, 2 derivatives with respect to 1, and the same thing coming from here is the same thing. So 2 phi, comma 1, 1, 2, 2. So that's the expression for that additional term. Right. The Airy stress function, for me at least, it's not as clean as the displacement-based approach. The displacement-based approach is quite, let me say, clean to work with. But eventually you will see, with this approach, we will be able to solve problems that otherwise would have been very cumbersome or perhaps impossible. It might look tedious, but the approach is actually rather clean. As usual, there is very little to memorize, or in fact, in this case, there is nothing to memorize here. So I don't expect you to sort of immediately remember any of these equalities or this final PD, right? So for the displacement-based approach, the situation was different because there the equations were very, very fundamental. So here, you don't have to memorize anything from the outset, but you need to always understand the solution diagram. That's why I'm drawing those diagrams so you keep in mind. Starting with the Airy stress function, satisfying equilibrium from the outset, we have imposed a restriction, which is the statement of compatibility. So now if I propose a phi, that will be some function, let's say polynomial in terms of x1 and x2, and it will have some free constants so that I can tailor it to my specific problem at hand. Those constants need to be such that when I evaluate the left-hand side, right, that's where those constants will appear. It has to be equal to that. So that is the restrictions. Those constants will be constrained by this compatibility requirement. Okay? And eventually, I will go ahead and solve for those constants. But I'm pretty much done. Okay? Together with the boundary conditions on displacement or stress, at this stage, in principle, I am done. Okay? But now, if I want to go ahead and actually evaluate the displacements, I need to take one more step. And as I have done here, so I just write something and you just believe that it works, and it does work, as you will see. For the displacements, perhaps it's a little bit disturbing, but I'm also going to write down an approach that works, sort of to simultaneously convince you and also to demonstrate the methodology. But it's a bit cumbersome, but again, it's eventually going to allow us to solve rather challenging problems. So, all right, let me go ahead and move on to displacement, since you do not have questions. Displacement. Okay, so my attempt to at least make you feel a little bit comfortable with what I'm about to write is to first start with a very heuristic, okay? I have little idea about what I'm doing. And I'm going to take an iterative approach. In other words, I'm going to propose something, almost stupid perhaps, and in fact, I will see that it doesn't work, and then I will make an attempt to correct it. So that's what I meant by heuristic. Okay. So now, my starting point will be to recall the relation between stress and strain in our 2D world. Okay. So because we're in a stress-based setting, it's natural to write the strain in terms of the stress. And last time we had derived this equality. Okay. Given the stress components, in-plane stress components, I can evaluate the in-plane strain components. So that's something we keep in mind. And now, first, I predict how the displacements will look. And I'll write naively here, right? I'm going to assume, right, I have a 2 mu here. Remember, these are terms like, for instance, U1, 1 for the normal strain 1 component, or U2, 2. So I have displacements here. In principle, I'd like to integrate both sides and eventually reach the displacements. So I will, for that reason, retain 2 mu. It's already on the left-hand side. And I will write 2 mu times U1 instead of directly U1. And eventually 2 mu times U2. And if I look back here, I have the stress. Well, 1 is phi, 2, 2. Sigma 2, 2 is phi, 1, 1. So that is something that disturbs me. I'm looking at the 1 component, but I'm taking a derivative for the 2 component, right? So here, in my naive approach, I will go for something more straightforward. And what I will assume is that since I'm looking at component 1, I'm going to take the Airy stress function and assume and hope that when I take its derivative with respect to 1, I will get somehow information about displacement in the 1 direction, okay? I have no idea whether it will work. I'm just hoping perhaps that is something that's meaningful. And just for the fun of it, I'll throw in a minus sign as well, okay, with an outlook towards what we're trying to do. Okay? And for U2 as well, it will be a minus phi, 2. Okay? Again, why did I put these? Well, I have a 1 there, I throw in a 1 there, I have a 2 there, I throw in a 2 there. That was the idea, really nothing too deep. But there are 2 problems here. Now, when I try to work with it, I can immediately observe them. And let me point out those 2 problems. OK, so problem number 1. Let's say there are 2 issues or problems. So the first one, and that's really not the important one, not the major problem, but it's certainly a problem. Remember that we can calculate, it's somewhat unfortunate that omega keeps appearing in my notation, but always there's a way to save ourselves. So omega 1, 2 was the 1, 2 component of the rotation matrix. Epsilon 1, 2 is the strain. Omega 1, 2 was the rotation matrix. And the way we calculated that was 1/2 U1, 2. And unlike the strain, instead of a plus sign, I put a minus sign, minus U2, 1. So that's the rotation matrix component, and that's the only component in our 2D world for rotation, because diagonal components were 0. OK, so now, one is associated with phi, 1, 2 associated with phi, 2. So phi, 1 comma 2, phi, comma 2, comma 1, a minus sign. Phi, comma 1, 2 minus phi, comma 1, 2, 0. Okay? So, which means physically that rotation about x3 axis is 0. Now, it might turn out that in our problem, rotation about the x3 axis is indeed 0. But the problem, the minor problem here is that functionally, my solution should permit small rotations. Okay? I do not want large rotations. They are not allowed. But small rotations should be permissible. Functionally, they should be able to appear there. In other words, from the displacements, when I calculate this, this should not, in general, be equal to 0. So that is a minor problem. But from the outset, with that formulation, they come out to be 0. So I don't like that. Okay? Maybe it's not a big deal, but if possible, I'd like to fix it. So here I will say that in general, rigid body rotation should be functionally, right? So permissible. Okay, and I'll highlight the word functionally. So mechanically for that problem, maybe they are 0 from the outset, but at least it should be my choice to set that rigid body rotation to 0, and they shouldn't be 0 from the outset. But that's not the problem. The major problem is with the stresses. Okay? So now, on the one hand, I have a relation between stress and strain, right? Now, the left-hand side, the strain, is a function of the Airy stress function. The right-hand side, the stress, is also a function of the Airy stress function. So somehow, when I evaluate the left-hand side in terms of the displacements, it should be equal to whatever I have on the right-hand side. And it turns out that when you take this and plug it in there, and when you take these, plug them in there, the equality does not hold. Okay? So let us instead of showing you that it doesn't work, I like to immediately proceed with the fix to the problem, and then also show you how the fix eventually is supposed to be formulated. So let me just note here that sigma 1, 2 is actually correctly recovered, but sigma 2, 2 and 1, 1 are not. So this is not true. Okay, so these parts for you, it's exercise, because I have a little bit more to work with. So at this stage, what you have to do is take these, evaluate the strain, and take the forms of the stress, plug them in there. And for 1, 1, they have to be equal. 2, 2, 1, 2, they have to be equal. And what you will find is that at this stage, sigma 1, 2 equals this will be satisfied. Okay? And on the other hand, sigma 1, 1 will not be equal to this. Sigma 2, 2 will not be equal to that. Okay? So the equality will be violated. So it seems that this naive approach has two problems. One, it doesn't give any general functionally a form for rotation, and the stresses are not correctly captured. So to fix these, I'm going to propose a form, an updated form for displacements. Okay, so I'm going to correct. And this correction is also with some insight. It's nothing obvious, but eventually it will work. And the correction is as follows. I'm going to add two terms to my original proposal. So this was my prediction. And now I'm going to add these two terms. Okay, so omega is our constant that appears, right, depending on whether the problem is plane stress or strain. It's a function of the Poisson ratio. Psi is some new function. And this psi is subject to a restriction. Okay, let me comment on that shortly. So here, Laplacian of psi must be equal to 0, and psi, comma 1, 2 must be equal to Laplacian of the Airy stress function minus 1 over omega minus 2 capital omega. So here I'll put my two remarks. This is your first homework to check that this doesn't work. And this is your second homework to check that these do work, okay? And that these are the restrictions on this function. So now, as soon as you're done writing, let me comment on that proposal. Okay, so, right, we're not living in an obvious world. It's just a lot of insight is being poured into these equations, and it's not my insight, obviously. It's whoever proposed it. But let me show you the idea. Okay, so the first idea was, as I already commented, this naive approach did not work. Actually, it turned out that the shear stresses were consistent with this proposal, but the normal stresses, 1, 1, and 2, 2, were not. And plus, we had the rigid body rotation problem. And now to fix that, I'm throwing in another term. This function phi is the Airy stress function. It has a name. This function psi, no name function. Okay? But the function cannot be anything either. It is subject to these two restrictions. And it turns out these two restrictions are needed for two reasons. Now, first of all, I need to make sure that with this U1 and U2, I need consistency with this proposal for the shear stress, and also for the normal stresses, these two equalities have to hold. Okay? So it turns out the first one is a requirement so that shear stresses are consistently captured. Okay? In other words, the shear stresses obey this equality. And the second one is for normal stresses. To make that a little bit more clear, let me demonstrate the consistency requirement for the shear stresses. And for the normal stresses, it's something you can do in a homework. Okay, so for shear, what I'm going to do is I'm going to go in and throw in here a 1, 2. Okay? That's also a 1, 2. And this term dies. Okay? So I have 2 mu epsilon 1, 2. And that is 1/2, right? U1, comma 2 plus U2, comma 1. Okay? So that's the left-hand side. And on the right-hand side, I have sigma 1, 2. Okay. So now I have two requirements. I propose a form for the displacement, and I have a requirement for sigma 1, 2. I'll plug in both of them in there. Okay? So for sigma 1, 2, what I want is that it is of the form minus phi, comma 1, 2. Okay? On the left-hand side, on the other hand, I have U1, comma 2, or in fact, let's split this up. We have mu U1, comma 2 plus mu U2, comma 1. Okay. Mu U1, comma 2. It is half of this derivative with respect to 2. So I'll do that. So this is 1/2 derivative of that with respect to 2. So minus phi, comma 1, 2 plus omega psi, comma 2, 2. And this one here is 1/2 derivative of this with respect to 1. So minus phi comma 2, 1 plus omega psi comma 1, 1. Okay. Right. So form of the strain, form of the stress. I plug in the requirement. That's my proposal for the form of the stress. And now this is my proposal for the form of the displacement and hence the strain. The two sides need to be consistent with each other. Okay? There should be no conflict. So now if I go ahead and evaluate further, so on the left-hand side, I have something, and on the right-hand side, I have something. The right-hand side is simple. Still the same, minus phi comma 1, 2. Here I have 1, 2 phi comma 1, 2's divided by 2, so minus phi comma 1, 2. And then I have plus omega over 2, psi comma 1, 1 plus psi comma 2, 2. Okay, and there you go. So these cancel each other. And therefore, if I propose the displacements to be of this form, for consistency associated with the shear stresses, I have the requirement that this is equal to 0. And this is nothing but the Laplacian of, let's say, Laplacian of psi. So that is a requirement on psi. Oh, yes. Thank you. Be a plus sign. Okay. So as tedious as it might look, at least we have a proposal. At least we can verify these additional requirements that we have. And all you have to do for the normal stresses, you have to choose as the indices 1, 1 or 2, 2. In fact, you will see that you can try 1, 1. You will get a requirement, which is this. And if you try 2, 2, you will get exactly the same requirement. So the requirement for either of the normal stress components, it's the same, and it is equal to that. All right? So if you want to construct the stresses, if you have already found out what the Airy stress function is, it turns out, therefore, it's not sufficient for a consistent result with our proposal for the form of the stresses. You need to also find the function psi. Luckily, we have some constraints for that function, which actually it's not making the process cumbersome, just the contrary. These constraints will allow us to eventually find what that function is. Again, I will have an example and you will see how all of this works. Okay? So if you remember, I had 3 goals. 1, to propose a form of the stress that a priori satisfies equilibrium. That is the Airy stress function. 2, we wanted to eventually formulate the compatibility requirement in terms of the Airy stress function, which is a constraint on the Airy stress function that will allow us to solve for what it is essentially. And that's what it is. And finally, now we have the form of the displacements. And I'm done with the problem, at least in a theoretical setting. So now for a specific problem, I need to go, and the very first step is to pick an Airy stress function. Now, I'd like to very quickly give you a perhaps too trivial demonstration of the fundamental aspect associated with the Airy stress function. In other words, often, not always, we will choose the Airy stress function to be some polynomial. And depending on the polynomial order, I would like to show you the resulting stress field so that we understand the basic relation between functional polynomial orders of Airy stress function and the stress. So examples for phi. And just for convenience here, I'm going to assume that the body force is equal to 0. I will, in order, choose 4 Airy stress functions: linear, quadratic, cubic, quartic. And the first one is linear. So let's say I choose the Airy stress function to be this. I'm saying linear. I still threw in a constant here. At this stage, what you should immediately recognize is that constants of the Airy stress function have absolutely no physical significance because the stresses require two derivatives, displacements require one derivative, and eventually, if you like to solve for psi, it also requires derivatives of phi, and therefore, this thing will always die. So this is of no significance. So really, I could have only put phi in there, A and B there. This is not necessary. So now, first of all, one thing we can recognize is that, actually, let me pull up this board. Right? So that is the form that I propose. The second step is to enforce compatibility. So I assume that the body force is equal to 0. So if the body force is equal to 0, compatibility requirement is gradient to the power of 4 is equal to phi. And that requires taking 4 derivatives. I have a linear function, which means that this form from the outset satisfies equilibrium. I don't need to do anything. All right? Now, perhaps, of course, however, it is too simple. Because if you calculate the stresses, as you see, 1 is phi comma 2 it is equal to 0. 2 is equal to phi comma 1 it is equal to 0. And sigma 1 is minus phi comma 1 it is equal to 0. So in other words, linear terms in the Airy stress function are of no good for the stresses. That's what I conclude. So if I want to eventually solve for the stress field, I might as well omit the linear terms and start with quadratic. So let's look at a quadratic Airy stress function field. So I'm going to skip so quadratic could involve linears, but I know what they do, so I'm just going to concentrate on the quadratic terms. So a x1 squared, x1, x2, and then x2 squared. That's the second proposal. Again, compatibility requires taking 4 derivatives and automatically satisfied, so I don't need to worry about compatibility. And now I can calculate the stress field. So sigma 1, again, I will write every time phi comma 2. So we have 2c. Sigma 2 is phi comma 1. It is equal to 2a. And sigma 12 is minus phi comma 12. So it's equal to minus b. Okay? So this is a uniform stress field. Okay? So if I look at my problem and I see that in this problem, there's going to be portions, regions of the stress where it's almost uniform. In my Airy stress function, I better have quadratic terms because uniform variations or uniform distribution of the stress can only be achieved by quadratic Airy stress function terms. So now I'm trying to build up an idea about how my Airy stress function should be constructed, right? Because that's the critical part. That's at the heart of the problem. And that's the toughest part, to propose a form of the Airy stress function. It's not too far, again, from the displacement-based approach. When I start the displacement-based approach, I think for a while, how can I simplify the form of the displacement? What shall I propose? And we've done that several times already. So here, again, we have to do that. But we have little experience with this new concept. So at least we are trying to build some understanding of its relation to the stress. So the third one is a cubic field. Now, by now, you can see more clearly, perhaps, that the stress field is always 2 orders less than the Airy stress function field. So if it's linear, there is nothing. If it's quadratic, it's a constant. If it's cubic, I'm going to eventually get a linearly varying stress field in terms of the coordinates. Okay. So up to cubic, I don't have to worry about compatibility. Again, compatibility has 4 derivatives, and therefore, all the derivatives vanish. If I calculate the stresses, phi comma 2, 2, right? So this is gone, that is gone, comma 2, 2, 2cx1 plus 6dx2. Sigma 2, 2 is phi comma 1, 1, so 6ax1 plus 2bx2. And sigma 1, 2 is minus phi comma 1, 2. So this term will die, that term will die, only these two survive. So minus 2b x1 minus 2b x2. So that's a linearly varying stress field. I'm sorry, this should have been C. It's 2cx2. Now, finally, although it is obvious, I'd like to now go up to the quartic as the last step, because in this, at least order, we have some non-trivial compatibility requirements. So quartic 1 would be that. And now let's go ahead and evaluate the compatibility requirement. So we need to evaluate the fourth gradients of phi. So that was phi comma, let me remind you, 4 derivatives with respect to 1, twice mixed derivative, and then 4 derivatives with respect to 2. So that is equal to 24a. Two derivatives with respect to 1, 2 derivatives with respect to 2. So that term dies away. That term survives, right? So we have 4c. And then 4 derivatives with respect to 2. And that should be equal to 0. Okay, so I'm correcting. I forgot to multiply by 2, so it's 8c. So now I have a non-trivial equation. And the form of the Airy stress function, this quartic Airy stress function, has 5 constants. And the compatibility imposes a restriction on 3 of them. Okay? So these constants eventually need to be chosen, or they need to be determined so as to satisfy this constraint. If I don't satisfy it, the implication is that I will have a solution with which there is no physical displacement field associated. So it doesn't make sense. I always need to have a physical displacement field. And that's why I need to satisfy this restriction. And in this case, if you calculate sigma alpha beta, you will have, of course, a order that is 2 orders less. So this is quartic, so the stress field will be quadratic. So now eventually, when I take a problem, at least if I suspect that the variation of the stress field is polynomial, then I will pick my Airy stress function accordingly. So let's say I suspect a quadratic field. I go ahead and throw in some quartic terms into the Airy stress function. If I suspect that there is some constant portion, I'll throw in some quadratic terms, etc. Okay? And that's how we're going to construct the Airy stress function. Questions? Don't worry. We'll play around with these concepts, and they will sink in. All right. So if no questions, then let's go ahead with the quiz. So thank you.